My name's Casey. I work for a startup called Netflix. We're a subscription service, not like a magazine subscription, more like more like a library. You get a library card, and you go into a library, and you get access to all of the content inside of the library. You can read books out of order if you want. I guess the difference is we hire people to act out the books. So really the value proposition for Netflix is that we save you from the trouble of reading. And like libraries, Netflix, it turns out, is very popular. So popular that over a third of the bits on the internet in North America are Netflix video traffic. And I could talk to you about our CDN, the world's largest CDN. But peer-to-peer cache invalidation, that's kind of a trivial problem to solve, and this is an architecture track, so I thought I'd talk about something a little bit more interesting. So I'm going to talk about our control plane. Our control plane is deployed in AWS in 3 regions, and it's a microservice. And I'm going to take a little bit to talk to you about what our architecture looks like, what our microservice looks like, because microservice means different things to different people. So here's a diagram of our microservice. We have 7 microservices, A through G. And at the top, you can see the icon up there represents a consumer device. So television, mobile phone, website, PlayStation, however you access Netflix, the service, you have some sort of device. And what happens when you access the service is a request comes in and hits service D. And service D doesn't have all of the information it needs to respond to that request. So D will reach out to C and F. And likewise, C and F don't have all of the information that they need to completely respond to their requests. So C will reach out to A, and F will reach out to B and G. And A will reach out to B and E, and G will also reach out to E and B. And you end up with that kind of like spaghetti communication that in green up there, those green lines. And then the results are all returned, and finally service D emits the response back to the client. Which is great, except for, again, all of that spaghetti communication, the IPC, the inter-process communication up there, is a little confusing. And I fibbed, we don't have 7 microservices, we have hundreds. Here's just the request for the streaming path, where the hollow circles represent microservices. I hid the labels because they're not important. And you can see requests coming in from the left-hand side of the screen, from the internet, and they hit that one node, and that's our proxy. And then the requests just fan out. And it gets kind of complex. So why would we do that? Why would we build an architecture that's complicated like this? So in a previous life, I was an engineering consultant and was privileged enough to see a lot of different architectures, a lot of different fairly large companies. And I noticed, this is just an observation, that most engineering organizations tend to optimize for one of these 3 properties: performance, fault tolerance, or availability. And we all know what performance is, so I'll distinguish between fault tolerance and availability. Fault tolerance you can think of as making sure that the state that you have is correct. So for example, a bank, fintech, insurance company, they're going to want to make sure that the state is correct. Whereas availability is making sure that the system is responding to user requests. So contrast like fintech or a bank, who are more concerned with fault tolerance, with like a massive multiplayer game, who's going to be more concerned with availability. And if the state gets corrupted, that might not even really matter. So usually I would see engineering organizations optimize for one of these things at the expense of the other 2. But more experienced engineering teams will optimize for all 3 simultaneously. Now there's some nuance in there because there's trade-offs. So within the context of the business requirements, you're going to want to optimize for one at the expense of the other 2 potentially, given your resource constraints. But finding a balance is great. And I was really excited when I got to Netflix because I found that they also optimized for this 4th property, feature velocity. And I've been at many organizations that optimize for feature velocity, but they try to do it through process, like Agile or Scrum or something like that. That's not what I'm talking about. I'm talking about engineering decisions that are made specifically to optimize for feature velocity. So for example, moving to the cloud so that we can focus on features rather than infrastructure, that's an engineering decision, an architectural decision explicitly made to optimize for feature velocity. Likewise, choosing a microservice architecture is a decision that explicitly optimizes for feature velocity. Because we don't have a monolith, we now aren't limited by the lowest common denominator of which component in the system needs to be updated. The microservices can deploy on their own cycle. And at Netflix, the engineering organization is a little bit different from most other companies I've been at as well, or that I've witnessed, in that it's easier for me to think of the engineering organization at Netflix as really being like 100 or so small engineering teams, say like 5 to 7 engineers each. And there's no like chief architect that ties that together. So each microservice is owned by an engineering team. And that engineering team is responsible not only for the functionality of the microservice, but also for its operational characteristics. So its deployment cycle, its uptime, things like that. So that's a complex system. And I want to dig into that a little bit. What do I mean by a complex system? Well, I like to call them unreasonable systems, because I find that gets under the skin of academics. A complex system, by its nature, is an unreasonable system. It exceeds the capacity of a human mind to comprehend the interaction of parts in any predictive capacity. So it's unreasonable because you cannot reason about it. So when I hear people say, oh, we're looking for a way to reason about this complex system, I interpret that to mean you're looking for a way to make the complex system not complex. And I think that's a very difficult thing to do. But I understand why you want to do it, because there are problems with complex systems. What kind of problems? Well, let's explore some. Let's explore some with the beer game. This is a big enough audience. There might be some MBAs in here who have played the beer game. I also played a beer game in college, but this is a different beer game. This is like a more... and if you're planning on taking an MBA, you might have to take a systems thinking class. And if so, I'm sorry, I'm going to ruin the whole class for you. So how does the beer game work? Well, in the beer game, there are 3 teams. There's customers, they like drinking beer. There are retailers, they sell the beer. And there are brewers who manufacture the beer. And the point of the game is to optimize for the customer's happiness and profit for the other 2 teams. Optimize for your own team first, but really you want everyone to be happy. And we need a story here. We're all engineers, so we'll say the product is foo beer. And if we were actually to play this, a professor, what they would do is they would divide the room into these 3 teams, and they would physically separate them. And you can only communicate to each other through slips of paper that you can write out intent or goods or money exchanged. So obviously, we're not going to do that because it would take too long to set up partitions. So I'll take you through a simulation of a game, very much condensed. You don't have to follow the numbers along here. You can if you want, but I'm just going to go through them very quickly. So here we have like 1 round of play. We'll call this week 0, where the demand for a case of foo beer is 1. And so a customer purchases 1 over the course of a week. A retailer has 2 in stock, so they have 1 remaining. They order 1. The brewer has 8 bottled, ready to go, and they're brewing 1 case. And so what you have here is a system in equilibrium, because the demand 1 on one side matches what's being produced by the brewer 1 case on the other side. So that's great. So that's our steady state equilibrium to start off with. Every story needs a protagonist. This is... I need a name. Nathan. This is Nathan the dog. So Nathan is a software engineer like us, very brilliant software engineer. And he's driving home from work one day and he says, you know what, I've got all of these brilliant ideas. I really just need to get over myself and publish them and share them with the world. So, okay, he stops on his way home, goes into the retail store, says, I want 3 cases of beer. Well, he's a software engineer, so what kind of beer is he going to buy? Of course, food beer. He can only buy 2 because the retailer only has 2, so I captured the missing sales as a -2 there. And the retailer wants to stay ahead of that, so they order 5 from the brewer, who wants to stay ahead of that, so they bottle 6. And he goes home and drinks both cases of beer, and he publishes the Food Beer Manifesto, which is brilliant. It's it's about the future of technology and how everything is going to live on serverless edge cloud drones on the blockchain. It's great, right? So it goes to #1 on Hacker News, so popular. He's famous. He starts planning his ICO. And because it's the Food Beer Manifesto, the next week there's an increase in demand, customer demand for food beer. So demand goes up to 64 cases. They can only buy 5 because the retailer didn't have any. The retailer, however, wants to match the current demand, so they order 65. And the brewer sees this, and they want to match what they see as exponential growth, so they start bottling 250 cases and add an extra distillery. But that weekend, every store needs an antagonist. I can't think of a name, so we'll just call him Project Manager. Project Manager reads the Food Beer Manifesto and says, oh my God, this is terrible, and writes a scathing rebuttal. It just destroys it. It's really short, though. It fits in a tweet, so I can actually read the whole thing. No, bad Nathan, no. And it gets a million retweets, almost brings Twitter down because it's so popular, and it's just like he's crushed, his ICO falls apart, his personal net worth goes down to normal levels. And so the next week, the only person who wants to buy food beer is Nathan the dog. So we go back to 3, but the brewer's case comes online, and the week after we go back to steady state demand of 1, and we end up with this terrible result. Again, the game was to optimize for customer happiness and profit. Instead, we end up with 61 cases that customers wanted to buy but couldn't. A retailer who has an extra 62 cases that they'll never be able to offload. Likewise, the brewery has 196 they can't offload, and an extra distillery. WTF are they going to do with that? Sorry, Nathan, such a sad result. So why are professors so mean? Why would they put us all through this? The game almost always ends up with this result. Usually there are a lot more rounds. It takes longer. Usually it's like a whole day or half day type thing. But it almost always ends up with that type of bad result. And for a systems thinking class, the reason that they do this is to specifically teach a type of effect called the bullwhip effect, where a sudden change in input has a big influence on output that's hard to recover from. And systems thinking is great about analyzing and giving us ways to think about these nonlinear effects. But the important part for us here is that none of the 3 teams were stupid. None of them did anything wrong. The decisions that they make as they play this are all very rational. And that applies directly to a microservice. You could have provably correct code in all of these microservices, and yet that still wouldn't protect you from aberrant or unwanted systemic effects. That's a property of a complex system. I can give you another example. We have a show called Stranger Things. Has anybody seen it? Somebody must have. Okay, one person's seen it. Cool. And when the first season came out last year, it was really cool. I was on a train watching it at night, so it was great ambiance for like kind of a horror thing. And I had my laptop on my lap and a coffee, and there was a scene that like I don't want to give anything away, but like I was a little, I don't know, surprised. And so like, went like that, and my coffee spilled on my laptop, and it stopped playing, and I, pull out a bunch of napkins, and I'm trying to dry it off, and it doesn't start playing again, so I do what any user would do. I hit refresh 100 times. But I'm on a train, so I'm probably between cell towers, and I don't know if it was the web browser or my laptop or what, they queue up the requests, and suddenly 100 requests go through to Netflix all at once. So what happens on the Netflix side? Microservice architecture, I saw the picture of that. I just want to bring your attention to two particular microservices. One is for personalization, which says, hey, for this given user, we know all this stuff about them, so we're going to show like, shows that you might want to watch again, or recommendations, or other things that are personalized to your experience to make it a better experience. And a customer microservice that just stores data for the customers. And these are built with distributed system best practices. And so, for example, the customer microservice is a cluster, and it doesn't store all of the data on each node, because that would be a lot. Then we would have to have very large nodes. So instead, each node has a smaller subspace of the data, and we use a consistent hash based on the user ID to figure out which node to go to get the data from. And we have fallbacks in place. So if personalization can't talk to the customer thing for whatever reason, it'll serve a default experience. Or if the customer microservice can't talk to the database, it can serve stuff from in-memory. And of course, we're on the cloud, and each engineering team is responsible for the operation of their own microservice. So to be responsible for our resources, they have scaling policies, intelligent scaling policies set up. Like if load gets low, then we shrink the cluster. And if load gets high, then we expand the cluster. So all of a sudden, 100 requests for one user come into the customer microservice, which uses a consistent hash to throw all the requests to one node. And that node says, whoa, 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 I'm having trouble talking to the database this quickly, so I'm going to flip into my fallback mode and serve things from memory. Cool. Turns out memory is a lot less CPU and I/O intensive than getting stuff off of disk. So the average load for the cluster goes down. So to be responsible about the resources, the ASG shrinks, terminates that node, moves its data over to another node. And as these 100 ones are going through, and now it's rebalancing that cluster, the personalization service on the 100th request gets bored of waiting for the customer microservice, so it serves a default experience that looks something like this. So now I'm on the train and I see this default experience. I'm like, hey, that is not what I'm used to seeing, right? Like, where's my Portlandia row? So I'm seeing something that I'm not used to seeing, so I do what any reasonable user does. I hit refresh 100 times. And so the same thing happens. 100 requests go to the same node, but it's a new node, doesn't have all the data yet. So it flips to serving things out of cache. The data might be a little bit more stale, but that's OK. It's faster, which reduces the average load for the cluster, so the cluster shrinks. But it causes more delay, so personalization now sends out its fallback, its default view for more users who see something that they're not used to. So they do what users do. They start hitting refresh. And now we have a user-induced retry storm. So now we've got all these users who are hitting refresh to try to get the proper response back, and it hits the customer microservice, which flips all of the nodes into serving things from memory, which drastically reduces the load, so that cluster shrinks to be cognizant of its resources, responsible about its resource utilization, and that ultimately brings the customer service over. That tips over, the personalization falls over, and that's how I brought down Netflix when Stranger Things Season 1 was released. Now, that's not a true story, probably. But things like that do happen, and what's the problem there, right? We can't blame the customer. Well, we can, but we can't blame the customer. So who's at fault? Nobody's at fault there, actually. The services were designed well, they were built well, and engineers are not omniscient. They can't predict these sorts of effects. So even though we can see in hindsight that there's a story about, oh, there's a vulnerability there, at the time, nothing was done wrong. The engineers were optimizing for the right things along the way, which is weird because we got a result that we didn't want. So who's the enemy here? Maybe it's complexity. I have a framework called economic complexity. I don't really have a name for it, so I picked economic complexity because, the framework was introduced to me by Kent Beck, and it was introduced to him by an economics professor, so maybe this is an economics thing. I'm not sure. But economic complexity, you can think of things that could intensify complexity or frustrate delivering a product. These 4 things: states, the number of states that a product or program could have, relationships between the elements that constitute or produce it, the uncertainty in the environment, and the irreversibility of your decisions. So the classic example of tackling states and relationships is Ford, where like you want a car, okay, we only have one kind of car. You get the one kind of car. And relationships where the manufacturers of the car, they didn't create like artisan cars the way they used to. They had assembly lines. So you knew exactly what the input was, and you knew exactly what the output should be. So for all of your Model Ts, you can measure your output at the end of an assembly line. Now, of course, you still have environmental uncertainty and market conditions. In software, we tend to not control for state because that's driven by roadmaps and customer requests. Relationships, in the case of complex systems, can grow unbounded between the parts, as you can see with the microservice example. The environment, there's not a lot that we can do about that. But irreversibility, we can start to tackle or perhaps tame. And so this is where moving to the cloud, moving to models of continuous delivery, and agile practices as opposed to like waterfall-ish stuff. Containers, serverless. This helps erode the irreversibility of our decisions, which gives us a leg up in handling complexity. So if you can make an architectural or engineering decision that helps make future decisions more easily reversible, that might help you in your battle against complexity. But again, is complexity the enemy? You can think of complexity in 2 parts, accidental and essential. Accidental complexity looks like this. It's a byproduct of doing work. It's like dirt on the floor. Nobody's bringing it inside the house on purpose. It just appears. Well, I have 2 kids, so sometimes they bring it in on purpose. But like, for most places, it just appears. Complexity just appears. And we can contrast that with essential complexity, which is designed into the system. So the interesting thing about accidental complexity is I don't really know of a good way to clean up after this in software. And it could be I haven't met the right people, or I'm just not exposed to the right framework. But it also seems to me that there aren't many software engineers who are aligned to tackle something like that. Not many people seem motivated to adopt practices of tackling accidental complexity. I know like one guy in my career who just really loves to refactor stuff. He's been writing a book on it for like 10 years and like just keeps rewriting the same. Sorry, Adam. But really, that's not like, you don't often hear that from engineers, that they're excited to or maybe conceptually they are, but I don't often hear that engineers actually do spend the time to go back and refactor their stuff to remove accidental complexity. It's particularly hard to do when you have deadlines and other pressures. And so then that leaves the essential complexity. About a year ago, somebody said that they wanted to choose a solution that was simple, given some options that we were considering. And I asked why, and he said, well, because I want it to be more available. And I had to think about that for a minute, and I strongly disagree that those things go together. I think best case scenario, simplicity and availability are orthogonal. Worst case scenario, they actually go together. So if I had an in-memory key value database running on my laptop, right, simplest thing in the world, and I asked you to make it more available and more simple, you couldn't. There's nothing that you can do. There's plenty of ways that you can make it more available, right? You can add consistent hashing and replicas, and you can figure out, with Chap theorem, are you going to optimize for the C or the A? There's a lot of ways that we know to make it more available. But all of them involve adding complexity. So if adding complexity is part of how we optimize for the properties that we want for a project, then it's probably not the enemy, and removing it is probably not going to do us any good. So if it's accidental, maybe, but especially essential complexity, focusing on making things simpler or removing that complexity might not buy you much. So far I've basically been describing the water. So what do we do about this? Well, what I propose is, instead of trying to eliminate or reduce complexity, we get better at navigating it. I'd go a step further and say, if you stay in the software industry, it will get more and more likely that you will be working on complex systems instead of simple ones. Systems where you can't predict how the system is going to respond to a particular environmental condition or input. So what do we do about it? Chaos engineering was designed to help navigate this in a particular way. So Netflix has made chaos engineering famous for two particular projects, Chaos Monkey and Chaos Kong. And I'm not going to dive into how the projects themselves work, but I'll describe what they do. So when we moved to the cloud from the data center, we had some incidents related to single points of failure disappearing. When we moved to the cloud, we moved to a system where we were scaling horizontally. So we drastically increased the number of servers that we were running on, and some of those instances would occasionally disappear. And if that was a critical service, then we would have an outage. And like I said, we don't have a chief architect at Netflix. We don't have a CTO either. So there's no mechanism, even though we know how to protect ourselves from things like an instance disappearing, there's no mechanism at Netflix for us to say, thou shalt. We can't take our best practices. We could list like a dozen best practices, right? Make sure you're deployed in, at least 3 AZs, and we could list a bunch of things. But we just can't tell all of our engineers, you have to do this, because that just doesn't exist at Netflix. There's no way to do that. So instead, what we did is we took the pain of the problem that we were trying to solve, instances disappearing, and we brought it to the forefront for all of the engineers. Chaos Monkey randomly will take one node from your microservice every day and turn it off during business hours. So if you don't design your system to be resilient to that, then you just won't get much done. So you fix that. Engineers are really good at that. The problem is right here. OK, I'll fix the problem that's right here. And then they can go on and focus back on their features again. And for years now, many years, we have not had an outage due to a single point of failure. So that was pretty powerful, small scale. So we looked at big scale, Chaos Kong. Same idea. We want to be resilient to outages at a regional level. Again, we're deployed in 3 regions. So if one of the regions goes down, or if we shoot ourselves in the foot because we stage our deployments by region, we want to move all of those users to the other 2 regions. And to make sure that we can do that and that we can survive that kind of incident, we run Chaos Kong regularly by turning off a region. Actually, we can't turn off a region. AWS won't let us. Something about having other clients. And if anybody knows where I can submit a feature product request to be able to do that. So we just simulate it very well. We simulate a region going down, and we drain all of the traffic from that region and send it to the other 2. So that's Chaos Kong. So these two were the start of chaos engineering. And we thought, OK, we're onto something. But what is this actually giving us? Well, here's another framework to think about what we're doing here. So Rasmussen has this notion that over time, a project will drift towards the things for which it has a signal. Economics, workload, and safety are the three primary signals. So economics is easy, and usually you can figure that out if you're a software engineer. You vaguely know OK, people cost money who are working on this thing, and there's cloud costs and stuff like that. And workload, if you have a good manager, generally you can see. You have some idea of oh, there's a lot of people working on this, or there's not many people working on this. And so over time, you will make your project more efficient for cost, or you will make it more efficient for operating it and maintaining it and stuff like that. But you rarely ever have a signal for safety, unless your service is falling down all the time. So usually, you don't know that your project is unsafe until you have an outage. And again, this is a complex system, so you can't predict when the outage is going to happen. You only know after it happens. So you don't get that signal. The entire time that you're getting slowly more and more unsafe, there's no way for you to know. But what Chaos Kong and Chaos Monkey are doing is they're providing you with a safety signal. And that keeps you from drifting into failure, and instead allows you to drift to a more successful place, a more available place. So when I first got to Netflix and I asked what chaos engineering was, the answer that I heard most often was, that's when you break stuff in production. I thought, well, that sounds really cool, but I can think of a lot of ways to break stuff in production that would add no value to Netflix whatsoever. Probably just make a lot of enemies. So we sat down and we decided to formalize this, and we created the document up there, principlesofchaos.org, that says this is what we think chaos engineering is, so that we know when we're doing it, how to do it, and how to do it better. And here's the rough definition. It's the facilitation of experiments to uncover systemic weaknesses. Experiments is an important differentiation from tests here. This, if you were to map out where this lives in computer science, it would still kind of fall under QA, although that kind of has a bad connotation in a lot of places. But it sits next to testing. So classical testing, this is my classical picture. Classical testing, if you start with a unit test, you have some input function, you assert some output. And for more sophisticated tests, well, you can just compose those. But you're making an assertion about something that you know or you expect. So that's classical testing. And testing and experimentation are not the same thing. Tests define the valence of a known asserted property. You're making an assertion. Whereas strictly speaking, tests do not create new knowledge. Experiments create new knowledge by nullifying a hunch. And that kicks you in the butt to go figure out what it is that you're seeing. That creates new knowledge. So chaos engineering falls into the new knowledge camp, whereas testing, I'm not saying don't test, it's still very valuable. It does something different. Best practices for chaos engineering: build a hypothesis about steady state behavior. So as engineers, we have the temptation, we want to know how things work. So we have the temptation when we find something that's wrong, we want to dig in and figure out, why is this working or why is it wrong? Chaos engineering wants to pull you away from that, because that kind of reductionist thinking doesn't help with complex systems. So instead of figuring out how something works, chaos engineering wants to focus on just whether it works. So we're looking for steady state behavior. For Netflix, it's easy. Our steady state metric across the business is how many video starts do we get per second. And that's a fairly smooth graph. So we can look at that steady state behavior to know whether or not the system's working. And if it's not working, then we have plenty of other tools and ways to figure out why it's not working. Very real world events. This captures the uncertainty of your environment. Experiment in production. Complex systems, you're dealing with unknowns that you don't know about. So it would be kind of foolish to think that you can articulate the things in production that you don't know about and to mirror them exactly in test. So not always possible, but we push on this pretty hard, and we run our experiments in production. Automate experiments to run continuously. This helps with continuous delivery and helps chip away at irreversibility. And then minimize the blast radius. So the point of chaos testing is not to introduce chaos. You're surfacing chaos that's already inherent in the system. So if you think that running an experiment is going to impact customers in a negative way, don't do that. Don't run that. Fix the problem first, and then run an experiment to see if you're right, that you are able to, that you are resilient to that condition. So those are the advanced principles of chaos. We seem to have pretty good consensus across the industry that this definition of chaos engineering is good and worthwhile. 3 years ago, we started running Chaos Community Day. We've had 3 of these now. The second one we held in Amazon's offices in Seattle. It was great. The last one most recently in San Francisco. And if you want to read more about it, you can go to principlesofchaos.org. So Chaos Monkey, small scale, Chaos Kong, large scale, but we've got this mess, this complex system mess. And we want to figure out how to take the same thing, the same advantages of getting that safety signal and apply it to a microservice architecture. So we created a program called Chap, stands for Chaos Automation Platform, and there are other talks on this and other blogs on it, so I won't delve into the details. But at a high level, what it allows us to do is select a service that we want to study, in this case, service C, clone it, create 2 small clones of it, deploy those in the cloud, because you see I have the little cloud shape there. And one of those is a control, and one of those is an experimental group. And we route our requests through the production stack, except for the requests that are in the experiment, a small subset of production. We route those to either the control or the experimental group instead of service C. And the rest of the requests are in production. So just for the thing that we want to study, we pull those out for these 2 groups. And then we apply some condition to the experimental group, like you can't talk to Cassandra, or all of your requests have 200 milliseconds, or you run at your SLA. That's an interesting one. And then that allows us to see, okay, again, our hypothesis is that we're resilient to whatever condition that we're introducing. So if we see our video starts diverge between the control and the experimental group, then we stop the experiment. And we go to the service team and say, hey, we thought we were resilient to this thing, and it turns out we aren't. Okay, and they can figure out how to fix that. So we give them that safety signal. So that's Chap. So that's chaos engineering. That's one way that we found that helps us navigate chaos without trying to reduce it or deprive ourselves of the advantages that complexity is giving us. Another one is intuition engineering. And this is kind of hard to explain. So I have a metaphor that I'll acknowledge up front is kind of absurd. But imagine you had a suit covered in electrodes, and the placement of the electrodes correspond to your microservices. And when you're on call, you have the privilege of wearing the suit. We affectionately call this the pain suit. So, for example, you're wearing the pain suit, you're on call, you wake up at 3 in the morning and your shoulder hurts, and you're like, damn it, login is down again. Our hypothesis is that after wearing the pain suit for not very long, you would develop an extra sense of the health, the state of the system, that you might not even be able to articulate why you feel that way, but you would just kind of feel it. So that I could say, hey, Nathan, how's the system doing? And he'd be, pretty good. Or something's off. And then we have other tools to figure out what's off, right? We've got metrics and monitoring and analysis to go dive in and figure out what's wrong with something. But we really like this idea of capturing a new sense of a holistic, complex system, again, in ways that you might not even be able to articulate. So we haven't built a paint suit yet, but we developed a visual analog. It's called Visceral. So here's Visceral. So the circle in the middle represents the internet, and the circles in the points of the triangle are the 3 regions that were deployed on AWS. And the dots moving between the big circle and the corners, those are requests coming in from the internet going to our 3 regions. And as long as you've been seeing this now, your brain has figured out what normal looks like based on the volume of dots, the color. Most of them are blue. Occasionally you'll see a red or yellow one. The speed at which they move. See if there's an easy way for me to play this again here. The speed at which they move, the direction, volume, color. Our brains are really good at processing a lot of data in parallel. So once we know what normal looks like, when we're in the middle of something, we can just glance at this and go, oh yeah, everything looks right. As opposed to going through our metrics. I mean, we've got the metrics. It takes about 42 time series charts to duplicate the amount of information that you get from this. So in an instant, you can just get it. And that gives you a new sense of the state of this system, holistically. So that's called Visceral. It's an open source project. And that's intuition engineering. So I am just a manager. So here are the people who actually do the work on the chaos team. And I hope I've given you something to think about in terms of complexity and whether or not you want to tackle it, navigate it, remove it, some frameworks to think about it in different ways. And we also wrote a book on chaos engineering. And the most fun part for me at a conference like this is taking questions, and we have enough time to, so I'm hoping you have questions. And we can start by just raise your hand, shout it out, I'll repeat it, and then I think we have enough time to actually man the microphones up here, if that's all right. Yes?
So each team is independent. How do you get them to add hooks, and how do you add the hooks for your Chap system?
So if each team is independent, how do we add hooks for Chap, the automation platform? Well, we do have common IPC methods. So we do have a failure injection library that sits at the junction between microservices. So each microservice doesn't create their own way of communicating with other microservices. We use things like REST and gRPC. And then we can just, there's maybe a handful of things that we know about, so we can build our chaos tools into those. I'm sorry, if you have other questions, you want to line up at the mics, that would work too. Yeah.
Hi, my question is the failure injection libraries and Chap tool, is that contributed to open source? And is it available for people to try?
Parts of it are, but generally no. So Chap is still a work in progress. Might get to a point where we release it open source, but right now it's really specific to certain aspects of Netflix's internal architecture that don't make it generally applicable across the industry.
Right.
So not yet there.
But are there plans?
We'll see.
Okay, thank you.
Hi. So this makes a lot of sense if you already have your domain split up across microservices, but without an architect to overseer type role, how did you initially split up the problem domain into the services?
So how did we transition from a monolith to a microservice?
Without an architect.
Without an architect. So I wasn't there, so I honestly can't answer that. My hunch is that we started off with architects. And are there any architects here? Oh, sorry. I see a world where architects are, and I don't mean any of you, of course, but architects in general are potentially less relevant. Because as we, as an industry, move to a place where we're all working with more complex systems, we're all going to have to get comfortable with that layer of complexity that can't fit in any human's mind. And in the old setting, what an architect was really good at was fitting all of the pieces together and understanding how they interact, such that if you needed to add a feature or add a component or change something, you could go to the architect, the wise one, and because they had the mental model in their head, they could say, okay, yeah, if you add this, then that's gonna, yeah, that's fine. Or no, well, you don't realize that there's this other thing that's gonna counteract that. We're moving, as an industry, we're moving out of that territory. So I think that accelerates the move from monoliths to microservices, but it probably makes it more difficult for us to go in the opposite direction.
Who are the people that are actually looking at Visceral and the node maps? Is it the engineers? Is it like almost like a business intelligence tool sometimes? Like who's looking at those?
So Visceral was specifically created for the traffic team, which is responsible for the remediation when one of the regions fails. So a region fails, the traffic team moves all of those customers through a combination of DNS and proxying and other things. And last year, that process took about 45 minutes. Just our control plane is somewhere on the order of 3% of internet traffic in North America, not including the video. So like moving from one region to the other two is a lot of traffic. So it took about 45 minutes. And so during that process, they needed a way to go, okay, moving traffic, okay, are the healthy regions still healthy? And if they had to stop and read 42 charts, then they might miss something. And in fact, there were cases where once we did have Visceral, they just glanced at that and said, oh, shoot, we have a problem. And they were able to prevent us from bringing the service down by having a more gradual, or fixing things. So initially, it was only used during incident remediation for the traffic team. At this point, the traffic team has gotten that process down from 45 minutes to closer to 5. So they don't even have time to look at Visceral. And I think intuition engineering, the power of intuition engineering, lives somewhere between you recognize you have a complex system and you're able to automate or machine learn your way out of that particular problem. And maybe that's a couple of years, right? At some point, I just want to be able to ask the system, hey, are you healthy? And it'll tell me. And maybe that's a year or two away. In the meantime, Visceral is a great way to provide the user interface to transmit that data to us. So I think intuition engineering will have a moving window in technology to bring people into the mix.
So you mentioned you have common hooks into failure and communication to enable some of this. Are there other important shared libraries or standards for services to enable chaos engineering or intuition engineering?
For us, no. There's a small group of consultancies now that specialize in chaos engineering. And we've spoken to many companies that have implemented chaos engineering in their own way. And usually that involves the same thing. They look for the IPC junction, or if you have like a service mesh, that's an easy way that, then you've got an easy target to focus on to start implementing it. But there's no like generic spec or like cross-industry spec for it. Yep.
So it seems a little scary to go impact production traffic and essentially affect your revenue streams, especially for more order-driven businesses. So how do you get a buy-in from product and people that aren't engineers, and how do you quantify the results of chaos engineering in such a way that they'll actually let you do these things?
So quantifying the results is not the most straightforward thing in the world, but getting buy-in, best way to do it is never let a good disaster go to waste. You will have a failure, right, at some point, and when you do, be ready and pounce on it. And hopefully, it'll be the type of failure that you can definitively say, had we been doing chaos experiments, we could have caught this. But even if not, you can say, here's a bunch of uncertainty. We're not even beginning to tackle uncertainty. So that's the best way to kind of justify it to people who are a little bit more removed from the problem and who don't understand that even writing good code isn't going to save you from these type of systemic effects.
Cool. Thank you.
The previous question was very close to what I was going to ask. I wanted to convince my company to run chaos monkeys in production, and they're highly reticent to do that. And so your advice on that was largely be ready to pounce on that next outage.
Yeah, so 3 years ago, we heard from financial institutions, oh, we can never do chaos at our place. We've got actual money on the line. You're just streaming videos. We've got real money. And we said, well, okay, but like you have these incidents anyway, so would you rather like learn about lost revenue or something that's going to impact money in a controlled environment, or are you just going to wait until like it happens and then panic? So fintech has taken up chaos engineering to the point where I believe it's ING, part of their internal auditing includes chaos engineering as a checklist, in their checklist as a check mark. To prove that their systems are good for lending and stuff like that. So a lot of Bank of America, Bank of Australia, Capital One, a lot of these banks now have chaos engineering practices. So then last year we heard from the medical industry, oh, well, sure, streaming video and money, we have lives on the line. We can never do chaos engineering with lives on the line. And that was great because that was a good opportunity to remind them that we're just implementing the best practices of Western science. This is an empirical process. We're setting up an experiment, and a controlled experiment, and we're running it. And that was pioneered by clinical trials. So the best example that we have of the empirical process is a blind, controlled medical study. They already do this all the time. They run experiments where lives are on the line. Now, I haven't convinced anybody to change their clinical trial program to a chaos program, but it's essentially the same thing. So now we're starting to see some uptake in medical institutions and hospitals and things like that because, again, they do have outages. They do have failures. It's just this is a way to control for it and to learn about it before it's really, really bad and so that you don't have to panic.
So as an architect trying to work himself out of a job, how do you get some of the commonalities in your service infrastructure that allow you to do things like Chap, pull a service out and run the experiments on a small subset of your production services?
So if you have a really heterogeneous environment with a bunch of different ways of doing communication between microservices, or you're not even talking about microservices?
Yeah, microservice would be a great example, but how do you get some of the commonality and consistency without central architecture?
Yeah, there's no magic bullet there for us. It was just one client library at a time, and then demonstrating that we could find results with the things that were affected by that client library, and then expanding. It didn't take us, we really only do two things with Chap. We either fail a call or we add latency. So we're just adding a tag in request context when a request comes into Netflix that propagates through the system. And at that juncture, it's just an if statement. If it has this, then fail it. If it has this, then assign this much latency. So it didn't take a lot of, it's all just typing, right? No, it didn't take a lot of software engineering to actually get us that. And it was just, divide and conquer.
Are chaos engineers embedded on the microservices teams, or is it a centralized kind of chaos engineering team?
Right now, it's a centralized team.
How do you keep the centralized team close to that intuition feeling of the services that are out there, or know what to necessarily go after which service?
It's a delicate balance because I don't want them to know too well the specific things to go after, because then they start understanding how the services work, and that takes their attention from figuring out whether the services are working. Macroscopically, we want to make sure that the service works, and so we don't want to get hung up on this microservice isn't doing what we think it should be doing. Because if the video continues playing, I don't care. We could have a bunch of microservices failing, but if the customer experience is still great, great. I don't want to get hung up on that. But they have to be good enough engineers and have to be familiar enough with them to know how to actually cause the failures. And obviously, if they spend all of their time looking for keys under the lamplight, then that wouldn't be useful either. So there's definitely a balance there. Cool. Any more questions? All right then. Thank you very much.